everyone, and for coming. And thank you, Marito, for again sharing. For coming actually on a Saturday. I gather for you a Saturday evening. So I'm, as I promised, I will talk today. The topic is the Higgs branch. And the first half of the lecture will be telling you what, at the moment, I think is sort of our understanding of how we get the Higgs branch from a geometric analysis. So thinking about it, starting from some Calabial singularity, like we discussed in the lectures 2 and 3, and then seeing how the Higgs branch structure could emerge. But then for the second half, being, sort of, I gather we should have at the end a little bit of fun. I'll talk about some sort of more ad hoc approach to the Higgs branch, which I think certainly there's something there, and I think it should connect also to the geometry, but I don't know at the moment how, and it would be very exciting to find out better how these things connect. And so this is basically, I'm going to show you some recipe how one can construct the Higgs branch, and the billion-dollar question, quote unquote, is how would you actually derive this from first principles? Okay, so that's, and I will show you some fun pictures. So that was a part of what I was saying. The first half is going to be a bit more, rigorous mathematical analysis to the extent that we can do in string theory. In the second half, I'll actually just throw lots of colorful pictures at you and some algorithm, and it'll be sort of up to you to then figure out how to make sense of it from first principle point of view. Okay, so the Higgs branch, we talked so far about the Coulomb branch, Higgs branch. Of course, here we're giving vevs to hypermultiplied scalars. And for conformal field theory, so in fact, hypermultiplied modular spaces are hyperkähler spaces. And I will always write the dimension in terms of quaternionic dimension and denote that as dH. And for SCFTs, so 5D SCFT, what we'd like to know is what is sort of you start again at the SCFT point, and you could now go into the Coulomb branch by resolving, for example, a singularity, or you can now go into the Higgs branch, and that what we'll see will correspond to deformations. And for SCFTs, the structure that we expect is actually that these are hyperkähler, so hyperkähler cones. And so one question is given a 5D SCFT, and you can construct it with whichever method you would like, what is the Higgs branch? And in particular, these hyperkähler cones, these singular hyperkähler spaces are in fact, they have a foliation structure. And what we would like to know is sort of that structure of these foliations. What we should also keep in mind is the full moduli space is another question. What's a full moduli space? And here, I mean, you have, right, we've looked at sort of the Coulomb branch. So this is, say, very schematically the Coulomb branch. Here's the SCFT. And then basically from here, there's sort of a Higgs branch emanating. But then as you go out on the Coulomb branch, it could be sort of subloci where there's sort of a Higgs branch prime, right? So for example, you go to a partial Coulomb branch, and then you could ask what's not a Higgs branch attached to that. An example would be you turn on the gauge cup when you go to a non-abelian gauge theory, like we discussed in the lectures, and then you ask what's the Higgs branch of this IR gauge theory. And that's of course something. Actually, why is this not showing? Is it stuck? Hello?
Hello,
yeah.
I see.
So, okay.
You are.
Something happened with the iPad, no?
Something's happened now. There's some
so let's see.
weird screen showing up.
Okay, let's see. Because I was writing and it stopped actually showing what I was writing. Okay, so I hope this is now.
Let's see. Now we can see screen again. Yeah, now I can see what you're writing.
Okay, fantastic. Yeah. So basically, so what I was saying, so for example, this line here could be in the Coulomb branch or sub. For example, this could be the non-abelian gauge theory locus, right? Where you turn on the gauge coupling and then you're asking what's the Higgs branch there. Now that's a question we can answer in classical, so just using defective field theory, but there could be sort of also decoupling limits in the extended Coulomb branch, right? So here we actually might want to actually put the extended Coulomb branch, and then the question is, how does the Higgs branch change as you now, for example, decouple hypermultiplet matter? And what's the full foliation structure of these Higgs branches over this extended Coulomb branch? So that's one of the questions I think that would be very exciting to answer eventually in the subject. So that's where we would like to go. Now, what is the challenge?
So Sakura?
Yeah.
So very quick question. Eventually you can also have mixed branches, right? Or not?
Yeah, so in fact, what I mean by this is when I write down this Higgs branch prime, this could be a mixed branch where you've gone into the extended Coulomb branch, and then you ask what is now the space of hypermultiplets
Right.
that I can turn on, right? So in fact, there's a full sort of at each point you could ask what is the Higgs branch?
Right, it's 5.
Space?
Yeah, I see.
Right,
okay.
so that's what I mean by this sort of very sort of rudimentary picture. And I think that structure is in fact something we don't completely understand yet, but there are certain things we can do. So what I will maybe able to show later in terms of some of the sort of structures that we've developed is that you actually can see how the Higgs branches change as we go from, say, a theory with a certain number of matter fields to the Higgs branch of a theory where one of the matter multiplets is decoupled. Okay, so what is the challenge? Is, of course, that there are quantum corrections. So there's really something wrong today with this, right? Now you don't see it
something now suddenly, it disappeared.
What happened? I have no idea. Okay, so worked so beautifully for 3 lectures, and now 4th lecture, it just totally, it's trying to connect. I don't know what it's doing.
It has some connection to the iPad.
Yeah, it's a connection to the iPad that's not working properly. So now you see it again, right? The iPad. Okay.
Now it's back. Yeah.
Okay. I am sorry. Let's hope that this is not a thing that will continue. So there are corrections to the metric. And in the M theory realization, these are due to M2 instantons, so M2 brain instantons that can wrap 3 cycles in the deformed geometry. And I'll explain that in a moment. But this just so you know, when you go back, that is actually the reason. And so the question is, how do you actually take these into account? And one way that has become sort of a tool that really came from various directions. One of the key tools that is to actually characterize the Higgs branches is what's called a magnetic river. And these occurred in sort of a variety of contexts, also very early on. I'm not sure I'm giving a full list. There were some papers by Horioguri and Vafa, where they study some Calabial geometries and also construct these quivers. And then, of course, very prominently by the Imperial group. So around Hanani et al. And I think Marcus might be in the audience again. And of course, Marcus has been also one of the people pushing this further, but from a more brainwave motivated perspective. And what I'd like to basically address is how can we really derive these things, these magnetic rivers, which are underlying the sort of construction of these Higgs branches from a geometric point of view. And so what is this magnetic river? Magnetic river is MQ. So very briefly, so the conjecture is, so this magnetic river is a 3D n equals to 4 quiver gauge theory. And as a 3D n equals 4 theory, it has its own Coulomb and Higgs branch. They're both hyperkähler manifolds. And the conjecture is that associated to, so there's a 5D SCFT has an MQ associated to it. And the Coulomb branch of this magnetic quiver is in fact the Higgs branch, the fully quantum corrected Higgs branch of the 5D SCFT. Okay, so that's the conjecture. And so key is understanding how you actually get this magnetic quiver. And then there are lots of tools to then study what actually is the hyperkähler foliation structure of that space. And so the question we'd like to answer is, so given a 5D SCFT, so 5D SCFTs given either in terms of brain webs, then there is some rule that is motivated from a brain web decomposition that then gives you this magnetic quiver, and that is also generalized in various ways to not just unitary quivers, but also OSP quivers. But if I'm giving you sort of in the brain webs, as you, and I'll discuss this very sort of in passing this correspondence, for some instances, these are essentially one-to-one with toric models. So toric Calabials, actually that's why I don't call it toric Calabials. Or more generally, what we call GTPs. So these are generalized toric geometries, toric polygons, sorry. In those cases, there's a recipe to get the magnetic quiver. And I will give you, and it's actually very algorithmic. And so that's very beautiful because we know exactly how to get it. It's just a question of now understanding why this is the right recipe. So this is sort of what I'll discuss in the second part of the lecture. In the first part of the lecture, I want to actually ask, given a 5D SCFT as M theory on some singular canonical singularity, like we discussed in lectures 2 and 3, how do I construct this magnetic quiver, right? So MQ, and that's a much more difficult question. And it's a more first principle question, how you actually go from a singular Calabial to the magnetic quiver. And there's, at the moment, we understand this in certain instances. And so one lesson that you should draw from these lectures, from this final lecture, is that the Higgs branch is probably much less well understood conceptually, how we get that. And so there's a lot of stuff to do, and I invite you to think about these questions. And there are many exciting things to uncover. So, okay, so while first talk about sort of this point one, what we know about the derivation of the magnetic quiver, and then we will go to the second part, which will be sort of more fun. I'm just showing you funny pictures and some rules, and they work. Okay, you should ask questions if there are questions. At this point, I don't see any questions. No. Okay, but you're still there because today it seems to be some connection issue. So let's start with sort of magnetic quivers or Higgs branches from X, which is a canonical singularity. And in fact, so the first thing to note is if you have X of this type, we've learned that there is X tilde, which is a resolution, or the many X tilde. So these are resolutions. And the relative Kähler moduli space is in one-to-one with the Coulomb branch. So this is a Coulomb branch phase, extended Coulomb branch phase. And there's another way, and Maurito mentioned that actually in a question in lecture 2, how one can go from a singular space to a smooth space in Calabial, and that's to deform it. And I'll denote this by X hat. And indeed, the deformations they give at least some hints. So this characterizes up to these quantum corrections the Higgs branch. So it won't determine the Higgs branch, but this will be important for the Higgs branch. And so what we have to study is the formations of Calabial singularities. And now if this singularity isn't an isolated singularity, so it's just at a point, right? So, but say there's a whole curve of singularities that connects to it, then these deformations may not actually be well defined. They might not be normalizable. So in fact, we'll restrict ourselves to study the deformation. We restrict to isolated singularities. And in fact, the simplest class are what's called isolated and hypersurfaces. Right, so there's just one equation in C4. And so I'll call these isolated hypersurface singularities. And these were actually classified by Xie and Yao, and also actually based on earlier work by Yao and Yu. And there are huge tables and classes of them, but all of them are of this type. So the singular space is some function, like we discussed one example in our resolution lecture. This is equal to 0 in C4. Right, so the x's are some coordinates, and now of course the question is what kind of f's are you allowed to pick? So f needs to be quasi-homogeneous. So let's call this here x underscore. So if I scale the xi with some lambda qi, some charge qi xi, then f of x of this lambda x. That's just going to be lambda f of x. So just maybe we should write it like this. So it just pulls out 1 power of lambda. And these qi, these charges, are rational and they're positive. Okay, so that's one condition. And then we want it to be isolated, as it's the singular locus needs to be isolated, right? So basically you check that f of x is 0 and all the if is 0, and this is basically a point. And then the canonicality, so that it's basically a canonical singularity, just means that the sum of all these charges needs to be bigger than 1. Okay, so that's the setup of the types of functions f. And an example we looked at, last lecture for this E8 model. And I'll come back to that model in a moment. Okay, so that's the setup. And now what exactly do we do with such hypersurface singularities? So now we would like to study the deformations. So unlike the resolution case, we're now really taking this polynomial, so x hat deformation is we start with this f of x, and then we add some multiples of monomials. So let's write this as something like this, until mu equals to 0. And now where can these monomials live? So these actually live in what's called the Milnor ring for this singularity. And so the Milnor ring is just you take the polynomial ring in all these 4 coordinates and then divide by the ideal that's generated by the derivatives of f. And mu, so this number mu here is just the number of all these possible deformations. That's a dimension of M, and that's in terms of, when you now ask what it is in terms of these Q's, this is just the sum of the Q, sorry, it's not the sum, product. 1 over Qi minus 1, and that's the Milnor number. Okay, so that's basically what the setup is. So now, what actually is now the geometry that we sort of, you've probably seen the conifold and you've resolved the conifold, but then you also now you can deform the conifold. And when you deform the conifold, so the conifold being just sort of a very simple equation like x1, x2 is x3, x4. When you deform, you introduce 3 cycles. And indeed, by doing this deformation, introduces 3 cycles. So in fact, the third homology of this x hat is just given by z to the mu. And so, right, this is what I was saying earlier. So if we put M theory on x hat, has now the potential of having M2 instantons on these 3 cycles. And they can, of course, give corrections to just this classical picture of these deformations. So some of these deformations may not actually be relevant in the description of the Higgs branch. Okay, so what we would like to do is now extract from this, so the structure of the Higgs branch. Now, it's not possible to do this because of these corrections, so it's directly studying the Higgs branch in 5D is difficult. So we actually need to revert to some potentially somewhat more elaborate methods. So in fact, what we have to do is we need to first study a related problem, and that's basically a 4D n equals to 2 problem, and then from there we will be able to extract what this magnetic quiver theory is. So you want to essentially from this data of these deformations, but also taking control of these quantum corrections, extract the Higgs branch in form of this magnetic quiver. Okay, so I should also introduce a little bit more before we do that, some more notation. So in fact, so given such a deformation, we introduce the spectral numbers, Li, or LL, because I read, so let's call it LK, and these LKs are just QK plus the sum of the QI minus 1, where QK is sum QI, and then from these MLI. So these are basically the M's, these M's here. These give us, it's a set of 4 numbers which give us powers of the xi in that monomial, and then we take the ith entry of that, and I should be here. This should be K. All right. And then the Higgs branch from sort of all the work of Gukov, Alpha, Witten can actually be described in just the dynamical hypermultiplets, right? Those where L, K is actually less than equal to 1. And in fact, counting these, only these deformations gives sort of the Higgs branch dimension, and that's basically the number of such deformations, which is the Higgs branch dimension for this theory. And in fact, this has 2 contributions. It has a contribution that I'll call R hat, and then another contribution which is F, and F is basically related to flavor deformations, and then R hat is actually in what we'll later see in 2B, or these strictly normalizable deformations. And what you should take away is there are these deformations in this of these equations. They're characterized in terms of monomials that are part of this Higgs branch, this Milnor ring, and of these, physically relevant are only a subset which satisfy this condition of the associated spectral number actually is less than or equal to 1, and that counting those gives us the actual Higgs branch deformations. But this doesn't tell us anything about the Higgs branch itself. And so what we really would like to know is the structure as hyperkähler cone rather than just the dimension of it. So how do we get the question that I said at the beginning that will guide us in our searches, right? So actually, how do we construct the actual hyperkähler space? And this will be via the magnetic quiver. So we want to construct a 3D n equals 4 theory that basically will give us the Higgs branch of the 5D theory. And the sort of proposal, and I think this is at the moment a proposal, and it works in many instances for these isolated hypersurface singularities, is the following. So we have some geometry X. So this is the singular geometry. And then we have X hat, which is the deformations. But so far, we've only looked at X in the context of M theory. And in fact, we should also consider the analog problem in type 2B. So in fact, I will just include this sort of mini overview, because I don't really have time to explain everything, since I want to also get. So basically, what the idea of this is the following. So not only are we planning to consider the M theory, right? So here we have this is what we studied. This is our 5D SCFT that we're interested in. And we put the M theory on the space X, which is the singular Calabial. And then we essentially would like to get to a 3-dimensional gauge theory. Now, the naive thing that you could do is put the 5D theory on a T2. You get a 3D n equals to 4 theory. Now, this is not the magnetic quiver theory, because again, this is sort of, it won't capture, in fact, all these quantum corrections. So there's no control that we have over those. But what we can also do is look at the following. We look at type 2B on the same geometry X. So this is sort of a new thing. This is actually a 4D n equals to 2 theory. So this is another way of doing geometric engineering, but now in the context of 4D n equals to 2. The key thing is we're keeping the same X here. So X is the same geometry. And now we can reduce that on a circle to 4D n equals to 4 theory. And I call this one, so EQ stands for electric quiver. So there's an EQ for the 5D theory, that's the EQ reduced, the 5D theory on the T2. And there's an EQ for the 4D theory, that's just the 4D n equals 2 theory reduced on a circle. Those are both 3D n equals to 4 theories. And now I can actually take this theory. So the key is to construct this theory. And then the conjecture is that if I now take a U1 to the F is the number of flavor, the rank of the flavor symmetry, a U1 to the F gauging, that's in fact the magnetic quiver for the 5D theory. And so it's motivated basically by the fact that this process going from the 2B to the M theory to the, oops, how does this happen again? Okay, so now you're gone again. Okay, so I don't know what it is today. Right, you don't see the screen right now.
Yeah, again, it's
I don't know what
disconnected.
happened.
Yeah.
It disconnected. So it says it's sharing, but it actually, okay.
Now it's back. Yeah.
Okay, so we start, so so essentially going from this 2B setup to the M theory setup should be some sort of mirror symmetry in this in the 3D series. So basically, right, this process of going from the theory, from this 5D theory on a T2, going to the electric theory, and then doing mirror symmetry, that's the magnetic river, that is modeled by going actually to the 2B dual, sort of, the M theory to A to 2B duality, so the T duality, and this U1 gauging should then exactly model the MQ5. And one question, of course, you can ask is, why is this now sort of a better way of sort of doing this? And the key is that, of course, this step here, right, sort of getting from a singular Calabial, doing the deformations, understanding in 40, this is the Coulomb branch, that's something that we very well understand. So this is a classic geometric engineering setup. So that's sort of just as an overview, but I want to now actually explain to you how we actually do this. So what this motivated why we should also look at the 2B theory on X. So actually, what do we know? We know about the 2B about the 2B on X, on the singular thing. Well, that's a 40 n equals to 2 theory. And in fact, these are nice, very often nice Lagrangian, often Lagrangian curve theories. So in fact, we can very often take these theories and then reduce them on the circle and then get a curve theory in 3 dimensions. And in fact, the Coulomb branch deformations of these 40 n equals to 2 theory, they're exactly modeled by X hat. And the Columbine spectrum, right? So I mean, this just explaining this is another lecture in itself, doing the geometric engineering for 40 n equals 2 theories. So at this point, I'm assuming that either if you don't know this, then that's really something worthwhile reading up on and learning. But this is sort of another framework of geometric engineering that I think since the, I don't know, since, well, very long time ago, since the 90s, I guess, has been developed on many fronts. So the Columbine spectrum is given by these charges QL that I introduced earlier over the sum QI minus 1. Okay, so we can, in fact, just from the geometry, the deformation space, extract the Columbine spectrum of these 40 n equals to 2 theories. So that's a pretty nice thing to be able to do. And of course, then checking sort of that the number of vector multiplets and hypermultiplets check out, that then gives us some indication what the resulting quiver theory should be. And then we still need to gauge with this U1 to the F. So
can I ask one question?
Absolutely, yes.
Can you compute this Columbine spectrum for arbitrary X or only for Turing models?
No, so this, in fact, we will compute. So we can compute this for all hypersurfaces, isolated hypersurfaces.
Oh, I see.
So this is basically for any of these f of x equals to 0 cases that I was so if we go back, so this basically, right, the condition and the condition is quasi-homogeneity, singular locus is isolated, and these charges are big, some to bigger than 1. And once you have these conditions, there's literally, it's a classification. Okay, it's literally some long-winded tables, And at this point, so this is some work we've been doing with I should say this, so we can determine that this is with Closet, myself, and Yina Wang. Sorry. Now, this is literally a database thing. So for any such hypersurface, it's a computational, you just chuck in the computer, and now it can calculate this Columbine spectrum. Now, not all of these will be nice sort of spectrum where you can immediately read off what the theory should be. So in fact, there could even be this is not always just an integral spectrum. So the, again, I have no idea. So there's some instability in the iPad today, which I have no idea what is the reason for that. Hijo, to answer your question, you can do this for any such hypersurface. And I will give an example of that in a moment. In fact, it includes all the E strings, and it includes some very sporadic, right? So the way we usually think about these series is we start in 60, we have some gauge series description, and they organize in this way. This particular way of structuring them is not at all clear how it works in terms of how the physics, the gauge series, the IR gauge series are related. So for example, you will find very sporadic, say, descendants of D-type conformal matter appearing as hypersurfaces. And the reason for that is that it's not clear what the criterion is that a given 5D SCFT has a description as a hypersurface. It's sort of some subclass of theory, right? Not every Calabial has that structure. In fact, toric, so because you were asking about toric, are usually not hypersurfaces, yeah? They're very complicated, complete intersections. So this is a slightly diametrically opposite to hypersurfaces. So, but let's actually calculate this for the E8 example. We studied in lecture 3. So the equation that we had was and in fact, we only looked at n equals to 1, but we can generalize this to any n. And why am I picking this one out? So the way I think you should think about this problem is you have a hypersurface, calculate the deltas, the Columbine spectrum, and then pick out those series that actually have an integral spectrum, and then try to reorganize it in terms of some quiver theory. And so for this particular one, I'm showing this to you because it has the following delta spectrum. It's nice integral Columbine dimensions, and the number of these is 8, 6, 4, 2, 1. This is for n equals to 1. And so the Q's, to calculate this, you need the Q's, which are just read off from the singularity, right? 1/3, 1/6, 1/6n. It's just the inverse to these powers. And capital Q is just 1 minus 1/6n. And from this, we can calculate the deltas. And now with this, because this is now integral, I can say, well, okay, so an SUN or M gauge factor contributes Coulomb branch dimensions from L minus 1 until 2. So now I can start, say, at 6, and then just take SU6, then there'll be an SU5 factor, right? There's 2 of these, so I've taken one for the SU6, and so that basically allows me to now sort of guess what actually the quiver should be. And in fact, this is consistent, so the spectrum, star spectrum, is consistent with gauge group SU6 times SU5 times SU4 squared, right? Because there are 4 of these now, times SU3 squared times SU2 squared. And now we still need to check, so the number of hypo is minus 16a plus 20c, and that's just 120n squared, and NV is 8a minus 4c, so that's 120n squared minus 9. And now this actually matches with the following quiver, so I can now draw out a quiver from this. So we have to start with an, say, n, 2n, 3n, 4n, 5n, 6n, and I'm running out of space. 4n, 2n, and 3n. And for n equals 1, it's exactly sort of, I didn't give you the full delta for general n, but for n equals to 1, it would just be basically an E8 quiver. So this is basically for n equals 1, this is an E8 quiver. And now note that here these are still in 2b. Here these are still SUM quivers. And I said the conjecture is that then by gauging U1 to the F, so the basic gauging, so here U1 to the 8, we get the magnetic quiver for the 5D theory. And in fact, the magnetic quiver for the 5D theory is just basically an E8 diagram with the Dinkin labels on it, with UN gauge nodes now, right? So in this case, this will be, so let me just write it down, 1, 2, 3, 4, 3. And now here, these are UM gauge nodes. Okay, so to maybe reiterate, this particular equation is nice in the sense that it gives us an integral Columbine spectrum, and it's consistent with a particular interpretation in terms of gauge groups and a quiver. If you pick an arbitrary hypersurface singularity in Yau and Yu's tables, you will not find such a nice spectrum, and it will be not integral. There'll be like fractional deltas. So then the interpretation is much less clear. And in fact, this is something that we in the paper recently tried to understand. When you have certain fractional deltas, how you actually supposed to now think in terms of the reduction to 3D, and how perhaps some of these flow to some integral values, but that's something we don't understand yet. So I think to answer your question, Heetal, in one sentence, just to summarize it, is we can calculate the deltas in all these examples, but we cannot always say what then the interpretation is in terms of a quiver. Okay, I think this is sort of the situation. So at the moment, we're picking out from a database all the ones with integral spectrum. Okay, so in fact here, this is now the quiver, this is the magnetic quiver for this theory. And now you can ask, what do you do with this? And so the magnetic quiver, the Coulomb branch of this magnetic quiver is now supposed to be the Higgs branch of this 5D SCFT. And in fact, so there are various rules how to now read off this Coulomb branch, and this is something that the Imperial group have sort of developed the tool set for. In fact, if you have such a quiver, the various things you can read off from it, from the magnetic quiver, so you can, first of all, you can of course calculate now what's called, this is monopole formula, the Hilbert series, and you actually from there read off the flavor symmetry of the theory. So, but more down to earth from this magnetic quiver, you can also read off the flavor symmetry from the what's called balance nodes. So the balance of a node is basically, so a node is balanced if so the node has a label, and it has basically this label n minus the sum of all the neighbors and I from the neighbors, 2 is equal to 0. Right, so that twice that node minus the sum of all the neighboring ones is 0. And those are all the balanced nodes, and the sub diagram of balanced nodes is GF Dynkin diagram. So in the above example here, right, so these are Dynkin diagrams, so in fact they satisfy exactly balance, right? So the balance is, right, so 2 times 1 is exactly 2, and then 2 has 1 plus 3, and so on and so forth. So in fact, in the above, you can read off that, in fact, this is DE8. This actually is indeed the magnetic quiver for the rank. This is the rank 1 E8 theory. We know this also from the resolution calculation we did in the last lecture. See the resolution computation. And this is confirmed by also the flavor symmetry for the theory. Okay, so that's the one way of extracting that. And for many of these hypersurfaces, that is possible to really derive, starting with this deformation story, and then computing the spectrum, the Columbine spectrum in 4D to derive the quiver. And there's some subtlety in terms of this U1 gauging, but that's actually it's something I think I've now largely under control. This is, however, and that's maybe sort of one of the limiting things, is so open questions here. What is the interpretation when the delta spectrum is not integral? And this happens, for example, for terminal singularities. And also, how do we study them? We study the magnetic quiver, this derivation I was just giving you from for more general geometries, for non-isolated singularities, right? And so we know, so one set of non-isolated singularities is exactly these elliptic models from lecture 3. So those are exactly, right, they're not isolated because we constructed them as collisions of, say, in E8 with an I1, right? So there's a whole set of E8 singularities coming in, there's this I1 coming in, so the SCFT that lives at this basically above this point certainly is not an isolated singularity. And so that setup, which in fact to our understanding is probably the most general setup, where you pick any 6D theory, you can construct a 5D theory. In that setup, we don't know how to study or derive this magnetic quiver yet. Okay, so that's an open question, and I think that would be something very interesting to explore and very exciting to explore. But right, even in the hypersurface case, there are many open questions because, right, the conjecture, I think that goes back to so that was sharpened really by Xi and Yao, is that really every such canonical singularity should be an SCFT. So when you actually have an SCFT realized by X, you should be able to say what the Higgs branch is. But then there's a question as to how to then extract it using this magnetic quiver approach. Okay, so that's actually halfway on today. So now I want to sort of, are there questions about this deformation story? So we talked about this, and I want to actually sort of slightly change tack and now say, well, this is all good, but there's sort of a complementary set of geometries where this is going back to lecture 2, where there are toric models. And in that case, there's an algorithmic way to really extract this magnetic quiver and thereby also the Higgs branch. And so that's something I wanted to discuss because it's computationally very nice and it's also very powerful. And it's Saturday evening for you guys, and you want to at least have some more relaxing, looking at some interesting quiver diagrams seems to be the right thing to do. But are there any questions about the what we talked about so far today?
Yes, may I ask about the Columbine generators that you've done in 4D? Or the
Yes.
Columbine spectrum.
Yes.
So what happens with them if you go to the magnetic quiver? Can you identify them with some generators of the Columbine or something?
Yeah, so basically, indeed, so what I was doing here is, this is still in 4D. Now from 4D, this is a 4D equals to the Columbine spectrum. Now I go on the circle, right, on S1 to a 3D, and it goes to 4 theory, which I call the electric quiver, for associated to the 4D theory, right? But then now this is a dimensional reduction, then indeed, now I have an electric quiver theory. This is still this is right in 4D, these were Lagrangian quiver gauge series for many of these examples. And I can do a reduction of that to just 3D. And this is now, when I'm drawing this here, this is basically the 3D quiver as well. And now I can calculate for this. So one thing that we need to do in addition is to gauge this U1 to the F. And that's basically going sort of doing this mirror symmetry to the magnetic quiver for the 5D theory. And that turns these SU nodes into U nodes. But I'm not
That's
sure
right.
Yeah. So this is still the spectrum for the 4D theory. Then I can read off a quiver, right? Because I know what each of these, so right, each of these, in this case, it's very nice. I picked this as a nice example, right? We can sort of read it off essentially from the structure, how many gauge groups we have. And in fact, we also check the number of hypers works out. And so then we get this quiver. And now I reduce that on a circle to a 3D and equals 4 quiver theory.
Also, the spectrum tells you what is the quiver, but it doesn't tell you what is the modular space in the end?
So it tells you what the quiver is. And now the quiver is at this point is the electric quiver for the 4D theory. And now I gauge an extra U1, and that gives you now with UN gauge, right? So this is now for the UM. Each of these nodes is now, and this is now the actual magnetic quiver. This is now the 3D n equals to 4 magnetic quiver as you know it. Okay, so why did, okay, so it did this again. I don't know, we will have to repeat this. I have no idea why. So that's the magnetic quiver as you know it. This is now the quiver that actually, whose Coulomb branch is the Higgs branch, right? So this object here that comes out of this process has now the Coulomb branch of that should be the Higgs branch of this. So what I'm doing here is I'm just deriving for a given geometry the magnetic quiver without using brain webs. Literally, you stick in a singular hypersurface, that's an SCFT, and then this is a way of extracting what the magnetic quiver is. And now, of course, you have all these tools how to study the magnetic quiver, right? Those are still apply. It's just the question is, how do you even get this object here? I'm not sure I've answered your questions, but can you, maybe you want to re-ask your question? What the...
I was just wondering whether the spectrum of the Columbine spectrum of the 4D theory, so if there's any relation to the so that the actual modular space that you compute in the end, so the finite quiver, whether the Columbine spectrum from 4D is realized as some sort of generators for this modular space.
I see. So you want to calculate already in 4 dimensions. So
maybe.
So, right, I think that this might be somewhat misleading because in general, this is not real. Okay, so in general, you have actually not even integral spectrum. So I think in this case here, it's very suggestive also because basically you have this SU, it's an SU quiver, And then all you're doing is gauging a U1 to the 8, and then you go to the UN quiver. But still, the moduli space for SU versus U is different. So I think you still need to do this gauging. The gauging is quite crucial in this process. So I don't think you can just basically stop here. Right, the electric quiver is not yet what we're after.
Okay.
I think this is basically this reduction for the integral Columbine spectrum. Basically, this is the electric. You're talking about the electric quiver, but that's actually not yet the final thing, because you still need to do what would correspond sort of to the mirror symmetry for these. You really need to still do this UN gauging to go back to the actual 5D magnetic quiver. But you know, this story is something really we're trying to understand. In particular, this gauging to really derive this from first principle is something that I don't fully understand yet. So this is something we see from examples, and example I know, okay, this is how you should gauge it. But that's what I'm saying. This story is much less firmly established, and I think, yeah.
Okay, thank you.
Yeah.
Can I ask a question?
Yeah, please.
Yeah, so you mentioned that for the 5D Higgs branch, you have M2 instanton corrections.
Yeah.
But on the 3D side, so the interpretation of on the Coulomb
so
branch.
indeed, very good. So now that's basically where the magnetic quiver, the power of all these tools that were developed in 3D n equals 4 comes to fruition, right? Because you might say, okay, so how, right? In fact, if you start here, you were telling me that all these corrections, how do you now deal with them here? And that's basically, so the key here is the main advantage is that here we have sort of tools from Cremonesi, Hanani, and collaborators, and also from mathematics, from Nakajima and Braverman, Finkelstein. Finkelberg, Finkelstein, okay.
Okay.
Finkelberg. Anyway, so what do? They calculate this exact, there's this sort of exactly the problem of incorporating the quantum corrections is solved in this 3D question, right? So that is ways of computing these monopole partition functions. So you really have computational tools to account for all of these quantum corrections. And that's why, right? So what you actually get, right? So what I mean is calculating out the Coulomb branch for this, we have the full, right? The expectation is this really captures now the full quantum Higgs branch, thanks to these exact computations in 3D.
I see. A monopole formula can tell you the quantum correction.
That's right. So the monopole formula basically in 3D solves this problem for you. Right. So one other way of asking this question is, of course, how would you write down a similar sort of exact expression in 5D?
Okay, thanks.
Yeah, good question. Any other questions?
So I have a quick question on the relationship between the type 2B on X that we see there in 4D and for these n=2 theories, and the related theories we can get by compactifying one of the 6D theories to 4D. I think we can get both n=1 or n=2 theories there using that construction of Larson. And I've heard there's some relationship between lifting up from the 5D theory here to a 6D theory that's sort of underway. Are there any comments you can make about that might be enough for us?
So basically, okay, so I'm not entirely sure I understood which 60 to 40s. Of course, these theories here can, for example, be engineered from 60 on like a class S construction, many of these theories. So some of them are also things with irregular punctures, like a Douglas series. It's not that this sort of automatically uplifts to 60 because these geometries, these isolated hypersurface singularities, where have they gone? These are not elliptic, and so or they're not obviously related to an elliptic model.
Right.
Right. So the elliptic model, and I try to sketch this at the very end.
Yeah, no, I think that's really a very different story. I was just wondering if there's any way to link this story to that story in cases where both sets of tools might apply, or
yeah. So that's basically this last question. Can you develop methods to actually study the Higgs branch in the situation when you have non-isolated singularities?
Right.
So you have, like a Cordara model, and you do a non-5 resolution, and then the question is, how do you now study deformations? And the problem is that because it's not isolated, a lot of these deformations will just be non-normalizable because you're just going in this flavor non-compact EA direction, for example, in this case, right? So the question is, how would you generalize those tools to that setup? And then there's a potential way of then going all the way back to maybe 60, but certainly in the IGEMs, there's no obvious way to relate it to these 60 models.
I see. So that step remains sort of unknown.
Yeah, I mean, of course, given a theory, so this is the rank 1 E8 theory, I know where it comes from, right? It's just that it's not, so, okay, in this case, we can actually be quite specific. So the isolated hypersurface singularity is this one. Mm-hmm. Now I can, of course, turn on more terms. I can write this out in terms of a non-isolated singularity, right? This is sort of, I can do that, but then sort of doing this analysis of these deformations becomes trickier. So it's related in that way that this is sort of the E-string theory, and it's this model that I discussed in the other lecture yesterday with the elliptic vibration and all this. It's the same SCFT. It's just in one case, I sort of really have taken all the flavor branes to really infinity, just completely decompacted and not there, and I've isolated just the singular geometry. And so the deformations really need that to really be sensible.
Thank you.
Yeah. So I think the answer is that's an interesting question, and perhaps one can try to understand this point here better, how one would sort of distinguish between these deformations that really are the deformations of the SCFT, and then deformations that are not relevant for the SCFT, but are just these deformations from these non-isolated nature of the singularity. So that's maybe one way of doing it.
Okay, thank you.
Cool. Any other questions? So now I want to slightly change gear, and so this is really I think I sort of gave you this story of the magnetic curves as if you are, oh, for God's sake, it just really doesn't seem to want to connect today. It's probably if I knew what the reason is, I would try to fix it. I apologize for this. Seems to be some connection with my computer. Anyway, what I was trying to say is the magnetic quiver here seemed to come from sort of some really almost roundabout way in the geometry. But if you actually go back to the very first lecture, to the second lecture, we discussed the toric models and the Higgs branch. That's going to be the topic of the second part. And in toric models, the Higgs branch actually has a very well running machine, and we can derive from these toric models the magnetic quiver. This is really an algorithmic procedure. And so then you'll ask yourself, so why didn't you tell us this before? Well, because it sort of is still in some way something that I think from the toric geometry point of view, we don't understand at all. It's just that, so how do we actually access this? Well, and the reason is that the toric models are dual in the sense of dual diagrams, right, to PQ5 brane webs. Right, so for example, our TNs will be sort of collections of 5 branes, sort of slightly scattered over widths in this collection of audience, because I'm definitely not the person who's the web person here, but this is the T3 model, and then you get a web that's dual to that. That's a 5 brane web where these are PQ5 branes, and these ones here are 7 branes. And so, and in this web story, there's a huge literature that says we can do a subweb decomposition, and that basically should be sort of like the possible Higgs branch deformations. I think there's still something to be understood. At the moment, I think this is also a set of rules that works. But now you could ask, what is that set of rules in the toric setup? And so, right, this is the work of the Imperial, obviously Imperial, but then also the Marcos is involved and many other people, Imperial related work, the Hanani and many others. But you could ask, what do these rules actually mean in terms of the toric geometry? And in fact, this brings us to something that's actually known in toric geometry from a very long time ago, that in fact, so Altman studied deformations of toric geometries, and said, well, if you have a strictly convex toric polygon, then, so for example, we looked at various examples, right? So these EN theories at low n are toric. So this was one of our examples, right? So this is the E3 theory. This is strictly convex. So strictly convex just means there are no vertices along any edges. So in fact, it means exactly it's isolated. And then the the deformations are characterized by what's called a Minkowski sum decomposition. So let's call the polygon P. And what is a Minkowski sum decomposition? So if I have 2 polygons, so the Minkowski sum of polygon P1 plus P2 is just the set of all the vertices of each of the 2 polygons, right? So just the sum of the eyes. Okay, don't need to write this down. This is basically what it says in here. Okay, so this is the Minkowski sum decomposition, and Altman, in just purely mathematical terms, then translated this into writing out some complete intersection for these simple toric diagrams, and then really started mapping these Minkowski sum decompositions into deformation. So what actually turns out, so in the lockdown last summer, I was trying to understand this, and these webs are really fantastic objects, and I'm still trying to get my head around these complicated webs, in particular with these O-planes, and many of you are much more experts than I am on this for sure. But what actually turns out is that the subweb decomposition from which one can extract this magnetic quiver is in fact related to this Minkowski sum decomposition. And I can sort of try to just simply understand what is that rule that generates from these PQ webs, the magnetic web quiver, in terms of these toric models. And this is sort of if you want to say this is just a method, that it's a translation into these toric diagrams, that's fine. But actually, it allows us to put this into a much more algorithmic, literally a computer program. And at the end of this lecture, I actually want to show you how this works in practice. And you can just download the code and play and generate as many magnetic rivers as you want. Because it's Saturday evening and that's what we should all be doing. Okay, so basically what we want to do is first maybe get some sense of what that means, this Minkowski sum decomposition. Okay, so let's look at this and I will just explain to you what the algorithm is to derive the magnetic river in this toric case. In this isolated toric case, and if I have time more generally, but this also works for what's called generalized toric or white dot diagrams. And so for the experts, when you have sort of more than one 5' ending on a 7', those instances as well. So in fact, this approach is as general as the web approach, at least for cases without any random defaults. So let's see how this works. So what is the Minkowski sum decomposition of this object here? I will first draw one of them for you, and then we'll see sort of what we have. So basically, Minkowski sum decomposition, if you're doing this in practice, it's really a fun thing to do. Basically, you just you take now this guy here, right? And now you can ask, how do I need to translate it around to generate the full things? In fact, I can now add this to, actually, this is totally wrong. I need to wait, this was the wrong thing. Actually, I need to, it's this one here. I was just wondering why this didn't work. So this one here plus pink orange and this one here. So how do I see that the Minkowski sum of these two is in fact this object over here? Well, I can attach to every point of the red one, the orange one, right? So indeed, I get this, I get these points, and I get these points. In fact, if I do this fast enough, you see the other one emerge. So this is the Minkowski sum. But in fact, in this case, there are two Minkowski sum decompositions. There's also the following, where I have this, so it's polygons, but the general polygons are basically just line segments, right? So line segments are also okay. And this, so in fact, that's another Minkowski sum decomposition. So this is just in terms of just basic polygon theory. In fact, you can again take the blue one and attach it, and then the purple one, and you see that. And now, what is the rule to get from this object now the magnetic river? So the Minkowski sum decomposition is essentially the subweb decomposition of a brane web. And what I do is I actually need to sort of implement that in the diagram itself. So the rule number one is we've done the Minkowski sum decomposition. And find all Minkowski sum decompositions. So in fact, having multiple means there are multiple branches in the Higgs branch. The second point is find a coloring. Construct a coloring. So the decomposition defines a coloring of the edges of the polygon, right? So for example, in this case of the green, basically we have this edge is this is blue, and this is purple. Okay, it's pink apparently. And now I need to also extend this coloring to the interior. So now in addition, extend the coloring to the interior by finding a decomposition into either irreducible triangles or, so in one color, or bicolored parallelograms. And so what I mean by that is that you have something like this, and then in another color, that, okay? So I just have to find a subdecomposition of the polygon such that it respects the colorings of the edges, and it goes into the interior and decomposes the polygon, it triangulates it, so to speak, into the respective either single color triangles or bicolored parallelograms. Okay, so how would we do this? Well, there's sort of an obvious thing that we could try. So basically, we have the option of, for example, extending this in here, and then having the green here, and then adding the blue here. And that basically does it for us, right? So now we've basically constructed 3 parallelograms and extended it to that. Now, we didn't look at both of our diagrams. Actually, let's also look at the first one, actually the other one that we needed to do. So the first one has red color on these edges. Now we need to think about how exactly this propagates into the interior. So in fact, we have this edge is here, this edge is here, this edge is here. And then the orange will be the other edges. Okay, so as I put them together, right, just to think of all these moving parts coming together, we get exactly the Minkowski sum decomposition. So that's basically coloring. I have these building blocks, and that induces a coloring of the edges. Now, how do I extend it to the interior? I have to do it in such a way that I get either single color triangles or bicolored parallelograms. And so I think this is, if I'm not mistaken, this is what we need to do here. So we have here 2 triangles that are red or orange, and then the other ones are bicolored. Probably should have picked some other color, but anyway. So that's step number 2. Okay, so I'm just taking you along this somewhat perhaps arbitrary sounding thing, but in fact, every single step has a precise meaning in the PQ5 brane web decomposition. And now the way to construct the magnetic quiver is the following. So for each color associates to a single vertex with a label 1. And now the connections, so the edges, are given by the mixed volume. Right, so we had these parallelograms, G, C1, C2, so color 1, color 2. So CI are the colors. So the mixed volumes of G, C1, C2 basically will tell us, so this is say for color C, this is the node for the color C, this is the number of edges between C1, C2, and what's the mixed volume? It's just the area, the total area between of these mixed colored polygons. So the mixed volume is just the area of bicolored parallelograms. Okay, so let's do this in our case here. So let me copy these down. And so what we find in this case here is that, of course, each one of these is volume 1. There's volume 1 here and here, but these are 2 colors of the same colors. So in fact, here we get a 2. So what we get from this here is we have 1 vertex, 1 here, 1 vertex, 1 here, and then here we have 1 vertex and 1 and 1. And now the edges we said are the bicolored polygon volumes. So in fact, all of these are connected by ones. And here we have two boxes from this and this contribution. So in fact, these are connected like that. Okay, and so this theory was, we studied that. We looked at this, and this was actually the E3 theory. And now this is the magnetic quiver. And in fact, from the magnetic quiver, we said from the from these, we can also read off what the flavor symmetry is. So in fact, these are basically the two contributions to the Higgs branch. So that's a reduced, so it has two leaves. And this is the A2 and the A1 minimal nilpotent orbits, closure of these, and so this indicates we actually have A2 times A1 flavor symmetry. Okay, so that's what we would get from this analysis. Now, of course, this was an extremely simple example, but this actually is indeed the magnetic quiver for the theory E3. So a nice and perhaps slightly more engaging example is, and that's sort of an exercise that's, I think, really fun to do, and it has much more structure, is to look at the octagon. So, and to do the decomposition in terms of colors and the many different colorings of these things. So determine the magnetic quiver for this, for the octagon. Okay, so this is, in fact, if you look at the internal vertices, right, this has a quiver interpretation in terms of two SU3 theories, gauge nodes, but just in terms of the magnetic quivers, it should be interesting to just do this example. Now, this method, in this simplicity that I gave you here, is in fact only applicable when it's sort of isolated. But in fact, this algorithm is generalizable to even non-isolated, right? And in fact, any non-isolated edge will add certain things to this magnetic quiver, and then and also dot diagrams, what we now call GTPs. It's slightly more formalized what it is, generalized toric diagrams. For these, there's also an equally precise algorithm. And for that, in fact, it's so precise that, in fact, you can literally chuck it into a computer, and perhaps something that for brainwaves well is something in the making. Here for these dual toric or generalized toric setups, we can just essentially do that. So what I wanted to show you is actually now stop sharing this iPad, which it seems to not like to do anyway, and actually start sharing the screen here and show you some computations. So, okay, so do you see the screen?
Yes, we can.
Okay, and so now so this is basically a mathematical code that you can download from the archive. It's attached to this paper with this extremely strange title. Don't ask where this came from. The symplectic leaves and 5 Higgs branches in the Polynesian tropical rainforest. The tropical rainforest comes from exactly this dual tropical curves or brainweb decompositions, and the symplectic leaves are just the leaves of these Higgs branches, and yeah, we're doing it with polygons, and so that's why it's Polynesian. That's that much for the explanation to this crazy title. So it's a code that actually, let me just quit the kernel, perhaps. Anyway, it doesn't matter. So there's a main code. You just run the main code, and then you can just in the code in the paper there are already examples. So what we have to give in is basically the polygon, and it's important to give it in an ordering that goes anti-clockwise, and so basically you just pick your favorite theory, whatever it is. It needs to have, you need to give it something that is convex, but it does not have to be isolated, and it does not have to be with vertices. That it can also have what's called white dots. So all of these can be implemented here. So let's look at E1. E1 is this example we started off with. So what it does is you chuck it in, and then sometimes there are some simplifications. These are just particular Hanani-Witten moves in the dual brainweb. And then it does the decomposition into the Minkowski sum, so to speak, right? So here you have this one plus this one gives you that diagram. And then using essentially this algorithm, or generalization of that, what I presented to you, computes the magnetic river. So that's the magnetic river this is the A1 affine Lincoln diagram. And so you have a U1 gauge series to connections here. And so similarly, so E2, we also discussed, this is sort of with one flavor added to the problem, and chucking this in, you get this diagram here. Then for E3, this is what we just studied. We in fact get, right, these were the two decompositions. You either have the two triangles or you have these lines, and it calculates the magnetic river. And then there's E4. So E4 is we add one more flavor, and then we expect, in fact, the flavor symmetry to be sort of, again, in this case, SU5. So you get the affine SU5 diagram for the magnetic river. Again, this is the decomposition. So all of this, and here we actually already starting to see, so until here, everything was strictly convex. And here you see this also, actually, this is now sort of an extension. So I haven't explained to you what the rule is to get to these. There's something you can read in the paper, for example. I'm also happy to answer questions about it in the final minute that I still have left. But here you have vertices along the edges. So this is not isolated, but it still, this of course has a Minkowski sum decomposition. And from this, we can compute this magnetic river. E5 is this box, and indeed you get the SO10 affine diagram. And then the first example that needs sort of a white dot, and these white dots are basically edges that in the toric, right, the toric diagram is embedded in Z2, and there's no actual vertex on the lattice point that sits on a line in the toric diagram. And in terms of brain webs, this means that there are 2 5 brains that end on the same 7th brain. And so even for these, right, so basically in the code, the way you implement it is you just, right, so going from, I think 5,1, you go from, let's see, 0,011, so we go up here, 5,142, and then there's just no vertex here, right? So here you would normally put in probably 2,1, and that's just not included. And then it automatically, right, the code will then say, aha, this should be a lattice point, but there's actually no vertex in the polygon, and so it puts a white dot. And then what this prune polygon is just putting it into a slightly nicer form using standard sort of operations on this generous toric polygons. So in fact, we're looking at the box like this, and again, it has a nice Minkowski sum decomposition. With these white dots, the thing becomes slightly more complicated, how to then read off the rules for the magnetic river, but the code does this for you now, right? So you don't even need to learn how to do it, you just chuck it in. Finally, E7 has this form, you see the E7 diagrams, E8. Okay, so now there are other examples that you can really look at these as you wish, but then, for example, like SUN with 5 flavors, you already get much more complicated diagrams. And one thing I should explain is here, the blue sub-diagrams in the magnetic rivers, those are exactly the balanced nodes. So these are the ones that actually will give the flavor symmetry. So if you go and you look, wherever you look up your flavor symmetries for SCFTs, the SCFT associated to SU3 level, transition level 1/2 with 5 flavors, and you ask what is the flavor symmetry, it'll come out as exactly A4 times SU2 times the U1, in fact, right? So there's always some rule of reading of the U1s. Okay, and then maybe one final thing that I want to, so there are loads and loads of examples you'll find in the code that's on the archive, but there's also one example that we have studied, which I think is the TN theories. So the TN theory, so for example, T4 is this example here. So you have just these triangles, and then this gives you sort of exactly something like what you would expect from like a trinion. You have a center node, which is the 4 that's not balanced, and then these legs that are balanced. And now, of course, the question that you might want to ask is for T3. I thought I had T3 as well, but actually there's no T3. So let me actually put in T3 just very quickly as the last thing. So for T3, we need 1, 2, 3. Actually, I have a little snippet for T3. Sorry, I will. Okay, 1 second. I'll give you the TNs in a moment. Okay, here we go. So if we look back at what we had here, so the T, let's just do this example here. So TN 3 are these vertices. You can write down, if you have some toric polygons, you just write a little snippet that gives you the polygon. Let's do the poly for analysis, and this is T3. And T3, again, you would expect this as center 3 node, and then these 3 legs with 2, 1, 2, 1. And indeed, and it also, of course, gives you that, in fact, it's not just the flavor symmetry SU3 cubed, but in fact, it's the full E6, right? To get the full affine E6 diagram here as the magnetic fiber. And the decomposition into subpolygons, in fact, there's only one right triangle, and you add that 3 times to itself. That's the Minkowski sum decomposition, and that's sort of one of the aspects that arise when you have non-isolated toric diagrams, that you have multiple of these building blocks. Okay, so what I want to basically say is that if you have an approach where you essentially say, okay, I'm not that interested in where it comes from, but I just want to know what the magnetic quiver is, and you have a generalized toric diagram, then this code will tell you exactly what the magnetic quiver is. But of course, really what we would like to know is, I can give you this toric geometry, and now how do you actually prove that these rules, these rules that I was talking about earlier for the isolated cases, actually are the rules how to determine the Higgs branch. And I think that's something that still needs to be explored. So that's, I think, what I want to finish. I'm 5 minutes over time, but I at least wanted to show you this sort of code. Okay, so are there any questions about this, about these, either these toric guys, or more generally about all the lectures? I can hear that's Maurizio breathing. Okay.
I just turned on my microphone. Okay, so there I get something on the chat.
What is the physical meaning of the adjacent matrix MQ in the 3D? It is so you mean this adjacency matrix here? This is just basically giving you this diagram. This is, in fact, this is not the code that you will see from the in the archive. This just, I actually use this to then feed it into another code to compute, for example, what's called the Hasse diagram. So the Hasse diagram is when, for example, you have, let's pick a more complicated thing, like this one here. You might not know what is now the foliation structure. And so you can use this adjacency matrix, right? So the adjacency matrix just has in the diagonal the vertices, and it gives you just the connections. So this is literally the quiver adjacency matrix of that 3D, and it goes for quiver theory.
So I have okay. I have a question. I have a question, but also there's some small announcement that I got a message from Wei that she said she wants to take a group photo at the end.
Okay.
I don't know how that works.
I don't know how it
but,
works either. Everyone, the camera's off, so.
Yeah, I
but-
can turn it on if they want, but yeah, okay.
Yeah, okay.
She had to explain, but now my question because my question is just very general, very.
Yeah.
So you show us these magnetic quivers and electric quivers for 5D theories.
Mhm.
So to my understanding, they are, if I understood correctly, they are kind of related by 3D mirror symmetry.
Yes, they should be.
So
I
that's
mean,
a proposal. That's a conjecture in
yeah. So
principle, right?
So basically, the 5D theory on T2 gives you a 3D also electric quiver. That's a 5D electric quiver, and then that has a magnetic, right, sort of mirror dual. But right, what in principle you should also be able to do it via string theory. Right, so you go from 2A from M to 2A, you go to 2B by mirror symmetry, and then you reduce that, and that should also therefore be related to this quiver we get in 2B as the electric quiver associated to 4D theory, so EQ4. And somehow this duality should be some gauging of U1s, but I can't tell you yet why this is sort of the right prescription from a purely 2B perspective. I don't know that yet.
But other properties of 3D mirrors have their interpretation in this 5D context, like for example, symplectic duality or these kind of things, or like category of modules of the quivers.
Yeah, so right, it's not that. So in 5D, I think it's just there is sort of some. So only the Higgs branch in 5D is hyperkähler, right? So only to that we have some associated sort of quiver in 3D, and the Coulomb branch of that is really this hyperkähler cone. You're asking when you have various, how are these things related? So I think, yeah, one way to answer that is it's some indirect relation to this 4-dimensional theory that's, you know, the 4D theory that comes from 2B on the same singularity. So these two things somehow have a relationship once you go to 3 dimensions. Right? But it's not a 5D, intrinsically 5D correspondence.
Right. That's why I was wondering. I see. That's great.
Yeah, I don't think,
very,
but yeah.
Well, it seems to be many open questions.
Yeah, certainly in this
exciting
direction,
subject,
there are lots of questions. Yeah.
Okay.
So I just have a very simple question.
Yeah.
So why your adjacency matrix is symmetric rather than anti-symmetric?
That's because there's basically okay. So you're asking, this is not the actual. So you're asking the answer to Xi Cheng's question is not quite. That is true. This is literally just because from this. Okay, for you, this you should take is just what I do stick in the Mathematica to actually draw this figure, and I'm not drawing the arrows going. I'm not drawing sort of arrows in both directions, and also this is literally then to feed it in later. So you should think about this diagram and think of it as a UN quiver gauge theory, right, with hypermultiplets and all this. Forget this. This is the physical meaning of this. It's literally a computational tool.
Okay, I see. Okay.
But you're right. So the answer I should have specified. It's not exactly that.
Can I ask one question?
Sure.
So yeah, you mentioned that for isolated hypersurface, you get how to obtain the magnetic quivers from geometry that is unitary. For some 5D theory, there is also UV dual to some theory which is made out of OSP quiver theory. Is there a way to get the this OSP theory from geometry?
So you mean when the magnetic quiver is an OSP, or
right.
So there are actually in the paper you'll see there's one example. In fact, it's a one hypersurface with powers 2, 5, 5, 5. In fact, again, it's a question of you have a hypersurface and then you can calculate deltas and then you get what you get. So when I see the set of deltas, sometimes indeed I can repackage them into unitary, but sometimes also into OSPs. So in one of the examples, this was actually sort of the theory that is the SCFT, which is G2 with 5 flavors, or there are many UV dual descriptions. That's actually an OSP quiver. So I don't know how I would now link it, but in the paper with Cyril and with Yinan, there's one quiver that's an OSP. But I think really it's sort of a, as I was answering also to Heachold, it's you have these hypersurfaces, and then I can calculate the deltas, and in some instances they have a nice interpretation. But I don't know, given a theory, how I would then construct the isolated hypersurface singularity. So it's a little bit like you have this huge class, and then studying that class, there are some points where I have such an interpretation, but there are many points where I don't. And they still should be CFT, so what are they? That's sort of another way of looking at that. But yeah, there are OSP quivers too. Yes.
Thank you.
Thank you. May I ask a question?
Yes.
Does there exist a situation that 3 different 5D SCFTs after each decoupling one flavor, they reach the same 5D SCFT?
So you start with 3 5D SCFTs that are distinct, and then you decouple and you go to one single point.
Yes, each of the 3, each decoupling just one flavor.
Just
is it
one
possible?
flavor.
Yeah, is it possible they reach the same?
Question. A very specific question. And I think the answer is yes, and I can maybe give you an example. I'm just looking at sort of the tables. And you just, so are you, okay, so. Okay, so I don't have a full answer immediately, so actually let me maybe stop screen share and let me see. So I think this is some, so can you maybe, while I'm trying to find you an example, give me an idea why you're asking this question? So
yep, because I understand a lot of examples there are 2 5D SCFTs
yes,
after each decoupling one flavor. Yes, so I currently are wondering, is it possible that's 3?
Yeah, so it certainly doesn't happen if you just have fundamentals, right? Because you're saying you just shift the transience level, say, by plus or minus a half.
Yes.
But I think if you look at other things, like, for example, the trees for the E6, E6 conform matter, you might find examples like that. I actually don't know off the top of my head, maybe someone else in the audience has an example ready, but I would think this is not disallowed.
So this does not happen at rank 2, right?
Yeah, rank 2, because in rank 2, everything is essentially SU2, SU3, or SU, but it's sort of, all of them are very well sort of established gauge theory, having a gauge theory interpretation with some fundamental antisymmetric matter. Of course, if you allow, yeah, so, but interesting question. You want them to meet at one point, so what would you have to do? I guess probably maybe the answer is it's not possible. Good question. Okay, I will try to, let me do one thing, let me think about it, and I will put it into at the end of my notes when I upload, when I send them to Wei. Who actually asked this question? Oh,
great, thank you.
Kairin, so okay, yes, I will think about it and put a message below at the end. I will write it down.
So can you think about intersection of two surface which gives Calabial 3?
Hi, Kimya. Good to see you. So what are you asking? You have intersection of two surfaces?
Yeah, instead of she and
Yeah.
just one surface, but can you have the same?
No. So in fact, no. In that the rank has absolutely no obvious relation to the structure of the equation. In fact, it's really painful to given a hypersurface to extract the rank without actually doing the resolution. So, in fact, with Yinan and we combined our resolution codes to really resolve all these hypersurfaces, and you really don't know until you've actually done the resolution. So, for example, you can get the example that I had. Maybe if I can continue screen sharing my iPad, if it allows me to. The example for the E8, that's actually that was rank n E string, right? So that's rank n. So where are we? You don't see anything at the moment. Here we go. So this example here, this equation is one of these hypersurfaces, and for n equals 1, it's a rank 1, but for n equals to generally n, it's actually a rank n E8 theory. So I can do n blow up, so there are n surfaces. So for n equals 2, you would get a rank 2 theory, for example, the rank 2 E8 theory.
No, so I mean two hypersurfaces of say 5.
Oh, I see. I'm sorry. You meaning complete intersect. So I take two hypersurfaces, intersect them. So there is indeed an extension. There's a paper, also Xi Yao and Yifan Wang and someone else I forgot. I'm really sorry. I'm terrible with names. There's another paper where they also explore the complete intersections, at least some examples. Yeah. And that can also be studied. So they don't look at resolutions or deformations, I think. It's just not at least in this context of studying the magnetic quiver. It's just that complete intersections are much harder to resolve. But yeah, that's possible. But I don't think they're classified. So I think the complete classification of isolated hypersurfaces is relatively complete, and there are some typos in Xi and Yao, but in the end, that's all there is. So we try to focus on that and see what kind of theories there are. Yeah, sorry, I misunderstood your question.
Okay,
Thanks.